8-bit non-wireless microcontroller creates an immediate bottleneck. Standard Arduinos limit you to just 32 kilobytes of RAM. Process complex sensor data or connect to the internet, and your system simply locks up. To get online, you usually have to purchase a $30 add-on Wi-Fi shield. Stacking those external shields quickly turns a compact prototype into a bulky, expensive tower of hardware. The ESP32 sidesteps this entirely by packing a dual-core 240 MHz processor, 512 kilobytes of RAM, and native Wi-Fi and Bluetooth into a single chip, usually for under $10. This chart plots base capability against cost. The standard Arduino Uno sits down here in the high-cost, low wireless capability zone. The ESP32 jumps straight to the top right quadrant, highly capable and incredibly cheap. For complex home automation or robotics, the ESP32 packs more processing power and connectivity into a smaller, cheaper package than the alternatives. But tapping into that power comes with a strict trade-off. You have to leave behind the highly forgiving 5-volt plug-and-play ecosystem. The ESP32 operates strictly on 3.3-volt logic levels. Wire a 5-volt sensor directly to the ESP32, and the high-voltage signal fries the microcontroller. To use older components safely, insert a logic level converter. This intercepts the 5-volt signal, stepping it down to 3.3 volts before hitting the chip. Because of its popularity, the hardware market for the ESP32 is severely fragmented. Buy it as a beginner-friendly dev kit, a surface mount W-room module, or just the bare system on a chip. Pick the wrong format for your specific skill level, and you'll end up with burned-out sensors or a custom-printed circuit board that refuses to boot. You need a precise integration strategy. The first integration path is designed for prototyping and intermediate makers. Going with an ESP32 dev kit gives you immediate software advantages over an Arduino. You get direct access to MicroPython, C++, and the ability to host a native web server right from the board itself. That flexibility is perfect for building automated watering systems or localized smart home hubs that need to talk to your router. The main trap here is quality control. The market is flooded with generic dev kits, and if you don't check the spec sheets carefully, you will run into frustrating pinout mismatches. You also still have to deal with the 3.3-volt rule, meaning you will be hand-wiring logic shifters for any 5-volt legacy sensors your project requires. Dev kits give you incredibly powerful software capabilities out of the box, but you have to accept a messier, physically bulkier hardware footprint. The second integration path is meant for advanced hardware integrators targeting mass production. By integrating the bare ESP32 chip directly onto a custom-printed circuit board, you massively shrink the unit's physical footprint and drop your bill of materials cost to around $2. The trade-off is total responsibility. You take on the burden of hardware stability, including managing complex RF antenna matching and tuning the crystal oscillator yourself. This official ESP32 reference schematic details the blocks needed to make the bare chip operational. The boot cycle demands a precise network of exactly 20 resistors and capacitors around the processor. You must also route an external SPI flash or PRAM component for system memory. Bare silicon delivers ultimate efficiency in both cost and size, but it strips away all of the dev kit safety nets and demands absolute precision in your circuit design. Whether you are building a custom PCB or modifying a dev kit, the single most common point of failure is the power supply scheme. Every time the ESP32 transmits data over Wi-Fi, it pulls massive, sudden spikes in electrical current. If your power rail is inadequate, those spikes cause the voltage to drop. The chip detects this instability, triggers a brownout reset, and endlessly reboots. To prevent this, Espressif's hardware design guidelines mandate that a single 3.3-volt power supply must deliver a continuous output of absolutely no less than 500 milliamps. Looking back at the schematic, you also need an ESD protection diode and at least a 10 microfarad capacitor placed exactly where the external power enters the board to smooth out those electrical demands. Getting reliable Wi-Fi transmission on custom hardware isn't a software issue. You have to over-engineer the raw power delivery to survive the transmission spikes. Succeeding with the ESP32 means being honest about your project goals, your skill level, and choosing the hardware format that matches them. This matrix maps out exactly which path you should take. If you are just starting to learn basic logic and you have a box full of standard 5-volt sensors, stick to the Arduino Uno R3. The trade-off is that you sacrifice native Wi-Fi capability. Specialized 5-volt tolerant ESP32 boards offer wireless connections at a premium. Intermediate makers should purchase an ESP32 W-Room dev kit, accepting the physical bulk of external level shifters. Advanced engineers use the bare ESP32 chip for rock-bottom costs, rigorously following the strict power rules. Moving down this list from dev kits to bare silicon is simply an exercise in trading convenience for absolute control. The ESP32 provides professional-grade silicon at a consumer price point. If you respect its 3.3-volt logic limits and meet its 500 milliamp power demand, this chip offers more raw hardware capability per dollar than anything else on the market.